Alrighty, welcome back. Let's talk about exponential function. An exponential function has a constant or an unchanging number as its base and a variable as its exponent. So it is in the form f of x is equal to a times b to the x power plus k, where a is not 0, but b is greater than 0, but it cannot be equal to 1. So some examples of exponential functions are f of x is equal to 2 to the x power, because you can write this as f of x is equal to 1 times 2 to the x plus k. So that does check out. And then you can see all of these over here. Yes, it's okay to have fractions as your b, as long as it's greater than 0. This right here, don't be fooled, because this negative is this -1, this invisible -1 as its a. The 5 is just the b, okay? So let's go ahead and classify exponential functions from 1 through 4. Number 1, automatically you can see that it's very similar to this one over here. So it is indeed an exponential function. So let's write exponential, because I can go ahead and rewrite this as f of x is equal to, or I should just write it over here, f of x is equal to a times b to the x plus k. So that works. This right here, number 2, this says f of x is equal to 3x plus 5. Well, we've been dealing with this since the beginning of the semester, and automatically that should tell you that's y equals mx plus b, right? So this is what we call a linear function. So this is a linear, and it's not exponential, because it's in the form f of x is equal to mx plus b, right? Remember, f of x is another way of saying y. F of x deals with functions, y deals with equations. So now, let's do number 3. This is f of x is equal to x squared plus 6x plus 9. So if you see something in this form, that means ax squared plus bx plus c, and you know that's going to be a quadratic function, because it's in the form ax squared plus bx plus c, right? Remember, when you have 3 terms and your highest degree is 2, that's dealing with a quadratic function. Number 4, f of x is equal to 2 to the x power plus 3. Well, looking at this and comparing it to the formula over here, or to the original function of an exponential, well, you can see that they have the same format. So for sure, this is an exponential function, because it's in the form f of x is equal to a times b dx plus k. All right, so now we're going to go ahead and graph exponential functions, and our example here is 2 to the x power. We don't know what an exponential function looks like. That's okay. We're going to go ahead and just see it by just graphing it right now. So remember the whole idea with functions. You have an input and you're given an output. Your x values are your inputs, and if you plug them into this function over here, you're going to get an output. So let's take a look at one of our inputs. I'm going to start off with -2. If x is -2, then I will write f of -2 is equal to 2 to the negative second power, right? If I plug in my inputs here, that means that anything on the right side, whenever I see an x, those x values are going to get replaced by your input, or in this case, -2. So let's take a look at this. We see 2 to the negative second power here. 2 to the negative second power, using our exponent rules, if we have a negative exponent, that means that we're going to have to flip, or we're going to have to move it to the imaginary, or move it to the other side of the imaginary fraction bar. So this can be rewritten as 1 over 2 to the second power, and 2 to the second power is what? 4. So 1 over 4, and I will put 1/4. Remember, y is the same thing as f of x, right? And our y value, or f of x, is 1/4. F of x is 1/4. Okay, let's do -1. So f of -1 is equal to 2 raised to the negative first power, and that's going to be rewritten as 1 over 2 to the first power, and we know that 2 to the first power is just 2, so this is going to be 1 over 2. So now we have x is equal to 0, so f of 0 is equal to 2 to the 0th power, and we know that 2 to the 0th power, anything raised to the 0th power is just 1. So that means your y value is 1 in this case. F of 1 is equal to 2 to the first power, which is 2. So I'm just going to write 2, and then f of 2 is equal to 2 to the second power, and that's just 4. So I write 4 there. Now, I'm going to go ahead and graph this function. I'm going to use my tables and just start plugging them in. Remember, we have our x values here and our y values here. We got ordered pairs. So this is just me saying -2, 1/4. But actually, let's just go ahead and start graphing the easier ones, and then we're going to deal with the fractions later. So let's just start with 0, 1. If I'm graphing 0, 1, 0, 1 should be right here, right? Because there's 0 as my x, and then 1 should be my y, so this is 0, 1. All right, so I'm done with that. Now I'm going to go ahead and graph 1, 2. 1, 2 is right here. So start putting a point right there on that grid, and you're done. And then 2, 4. 2, 4 should be right here. This is 2, 4. And then I got the easier ones out of the way. Now I'm going to go ahead and deal with the fraction. So let's locate where -1 and -2 are, because I'm dealing with my x values, and I'm going to go deal with my y values. -1 is right here, right? It's before that 0, so I will put -1 right here just to show you. And then before -1 is what? -2. Okay, so then what the heck? We're dealing with fractions here, and how are you able to graph these? Well, we know that if we're looking at the y values, remember the y value is that horizontal line, not the horizontal, the vertical line going up and down. We can see that here's my y value of 0 and my y value of 1. And we know that 1/2 is just another way of saying 0.50, right? So 0.50, that's half of 1. So we know that if I want to graph -1, 1/2, it's just simply that. Okay, and then graphing -2, 1/4. 1/4 is like what? 0.20, right? No, 0.25. I'm sorry. So we know that that's going to be between 0 and 0.50. So it should be right here. Okay, now if you have all those points ready, go ahead and start connecting and draw arrows on both ends. This is not perfect. But it's good enough. And then draw the arrows. There you go. So this is what an exponential function looks like. It starts slow. It starts small, but when it hits a certain threshold, it's going to skyrocket. So let's go ahead and determine our domain and our range and our y-intercept and the horizontal asymptote. And you're wondering, well, what the heck is a horizontal asymptote? I will get there. So our domain, we look from left to right, right? It's the set of what? All x values, right? So let's write that down. That is the set of all x values. And, if I have arrows on both ends, eventually it's going to touch every x values there is or there are, and it might take a little bit to reach every x value, but it will get there. So we say that the domain for an exponential function should be all real numbers. And then I'm not going to go ahead and talk about the range, because I want to go ahead and just jump to the horizontal asymptote. Now, the horizontal asymptote, it says that we have an imaginary horizontal line that a curve approaches. We're talking about this curve right here, but doesn't touch it. So it is always y equals k. Now, let's go back to this function over here. F of x is equal to 2 to the x power. I am going to rewrite it so it looks like this, right? F of x is equal to 8 times b to the x power plus k. So rewriting this should be f of x is equal to 2 to the x power plus 0, right? 0 is our k, and writing this, it doesn't change anything, right? 2 to the x power plus 0 is still 2 to the x. But I'm trying to make clear of what our k value is. So our horizontal asymptote will always be y equals k. So I'm going to write y is equal to, so what is our k value? This 0 is our k, so I write y equals 0. Okay, now I'm going to go ahead and draw my horizontal asymptote. And let's use a different color to show you what the horizontal asymptote. If it's y equals 0, you should know that, like at the beginning, if we are graphing something that's y equals something, it's going to be that horizontal line, and it's going to be right here. It's 0. This is 0, so I'm going to go ahead and draw an imaginary dashed line. I'm going to use a different color to show you what this is. Okay, this is our horizontal asymptote. Again, if we take a look at this, graph, or if we take a look at this particular function, it will approach this imaginary line, but it will never touch it, and that's what the asymptote is. This line will never, ever go over it will never go over this asymptote at all. Okay, so if it's approaching this asymptote, it means that it's not going to be hitting 0 at all. Our function will never have a y value of 0. So what does this indicate for our range? Well, again, if everything is above this horizontal asymptote where, this line doesn't touch at all, how would I figure out my range? And our range is we look from, bottom to top, right? So it should mean that all of my y values is great. All my y values are greater than this horizontal asymptote. So I write y is greater than, I'm not supposed to put it in y-intercept. Y is greater than 0, right? It is not y greater than or equal to 0. It's y greater than 0. All the y values are included, but not 0. So hopefully this makes somewhat sense. So if you have any questions, just pause and just think, and if you have access to the internet, which you should because you're watching this video, then go ahead and do some Googling or watch some more YouTube videos on what the whole idea of asymptotes are. Y-intercept. Well, we know what the y-intercept is. We talked about it a lot. Nothing should change in terms of exponential function. It's the same idea. The y-intercept is where the line crosses the y-axis. And all we do is set x is equal to 0, but we're not going to go ahead and set x equal to 0 because we can just take a look at our function, and it's always in the form what? 0, comma y, right? So which one is in the form 0, comma y? Where does that line touch? Well, it touches right here. What is that right there? That's 0, comma 1. So that means my y-intercept is at y equals 1 because 0, comma 1. And then we're done. Okay, so when it comes to, let's take a look at what it says over here. It says observation, exponential functions start small. Yes, they start small, but when it hits at a certain threshold, it's going to start growing faster or exponentially. Only certain values are useful when graphing exponential functions. Usually, it's best if we use x is equal to 0 and x is equal to 1 for our inputs, because we know that anything raised to the 0 power, right, is just 1. And it's just easier to graph that way. And then x is equal to 1. Why? Because, well, if you are given 2 to the first power, then that's just 2. If you just change your base and then make it a 3 to the first power, it's just 3, right? It's always that. If you have a base raised to the first power, it's always going to be that base. So that's why it's just so easy to just use it's easier to use x equals 0 and x equals 1 as your inputs. Okay. Now let's start graphing things where we have an a value. So I'm going to go ahead and just rewrite this as f of x is equal to 3 times 2 to the x power plus, and then remember our k value, 0. So automatically we should know that our horizontal asymptote is just y is equal to 0, and our range should be y greater than 0, right? This is always y equals k, and this is always y greater than k. And then domain, well, I'm going to worry about the domain and the y-intercept later. Let's just go ahead and start plugging these in. So, remember, you have a calculator for this. You can use that y equals button and see if you can, get these y values faster. So let's write 3. So if these are my inputs, we can figure out our output. So I'm going to write f of -2 is equal to 3 times 2 raised to the -2nd power. And I'm just, that kind of looks like 3 times 1 over 2 to the 2nd power, which is just 3 over 4. Okay, so I'll write 3/4 there. And then f of -1 is equal to 3 times 2 raised to the -1st power. And then that's just 3 times 1 over 2 to the 1st power, and that's just 3 halves. So I write 3 halves there. Okay. Let's see. Let's write f of 0 is equal to 3 times 2 to the 0 power. And then 2 to the 0 power, that's going to be 3 times 1. We know that's just 3. F of 1 is equal to 3 times 2 to the 1st power. And that's just the same thing as 3 times 2, which is just 6. And then f of 2 is equal to 3 times 2 to the 2nd power. And then that's just rewritten as 3 times 4, which is just 12. Okay, so hopefully I am not making any mistakes here. If I'm making mistakes, that's kind of sad. Okay, that's fine. This looks fine to me. So let's start graphing the easy parts first. These are whole numbers, so I'm going to go ahead and graph the whole numbers. So 0, 3, which should be right here, and then 1, 6 is right there, and then 2, 12, that's just going to exceed the graph, so I'm just going to say that 2, 12 is right there. It's not perfect. I don't have enough room, but we can just say that that's 2, 12, even though that looks like 2, 11. So now I'm going to go ahead and start graphing these. Remember, the number before 0 should be -1, and then the number before -1 should be -2, and I'm going to start graphing. So let's start with 3/4. 3/4. Hold on, let me check something real fast. Is that good? Okay, cool. So -1, or not -1, -2, 3/4. 3/4, that's 0.75. It's the third quarter, or 70. If you have 4 quarters and you have 3 out of 4, that's like 75 cents. So it should be right here above that 0.50. And then 3 halves. 3 is greater than 2, so for sure if we take a look at it, or you can put that in the calculator. 3 over 2, that's somewhere around like 1 point something. And listen, I can't do the math in my head, and I could care less on what that really is, but we know that 3 halves is somewhere around 1 point something. So let's just put it right there. Now I'm satisfied with the points. I'm going to go ahead and start graphing, or not graphing, connecting those points. Just like this. Good. And then don't forget those arrows, because it's going to help you figure out what your domain is. Your domain, if we take a look, we read from left to right, eventually it's going to hit every... Oh, whoa, there you go. All right. So domain, we look from left to right, set of all x values, so that means it's going to be all real numbers. And then the y-intercept, we can see where the line crosses the x-axis, or not the x-axis, the y-axis over here, 0, 3. So I write y is equal to 3 or 0, 3, and then you're done. You're done. This is your exponential function, right? So now we're going to go ahead and talk about tables. Linear functions have a constant rate of change. Remember, that's our slope. Rate of change is another way of saying slope, adding by the same number each time. So this should not be new. You've done this at the beginning. And then we're going to introduce exponential functions, have a common ratio. You've done that before. We teased you with that before at the beginning, but we didn't really explain what that really is. But now you're going to know, because that when you have a common ratio, when you have the number multiplying, if you're multiplying by the same number each time, then you're going to have an exponential function there. And if it's not, if it's not any of those, then you just say it's neither. Number 7, we're going to go ahead and look at our pattern here. We can see that, hey, this is going, for our x values, is going by, +1 each time. And then over here, we can just subtract 3 on both, or for everything. And then remember, the slope is the change in y over the change in x. The change in y over the change in x, right? y2 minus y1 over x2 minus x1. So you can rewrite that as -3, 1. Your slope is -3. So what does this indicate? Well, if I'm adding, remember, this is the same thing as, subtracting is the same thing as adding, plus -3 plus -3 plus -3, right? So that means you're dealing with a linear function over here, because you are adding by the same number, or in this case, you are subtracting by the same number here. So that's indeed a linear function. B, on the other hand, okay, well, I'm looking at my x values. I have a constant of adding 1 each time, but here I am subtracting and adding, and everything just seems so inconsistent. It's neither, because I am not adding by the same number, or I'm not multiplying by the same number, so it's neither in this case. Let's do C. I'm just going to add 1 each time, and that works. And then here I can see a pattern, because 5 times what is going to give me 10? That's going to be, 2. 5 times 2 is 10. 10 times what will give me 20? That's just going to be times 2. And then you can see the pattern over here. I'm multiplying by 2 each time. This is what we call a ratio. If I'm multiplying by the same number, so this is a ratio of 2. If I have a ratio here, that indicates that I have an exponential function. All right. That's all for the notes here. So if you have any questions about this, feel free to ask me, or there are plenty of resources online that you can check out. See ya!